All right, so last lecture we had this sort of blindingly quick, eccentric view of the ergodic theorem from finite state-space Markov chains, and I described it all in terms of just spectral theory, eigenvalues. Basically, if you have the situation where there's a single eigenvalue at 1, so no repeated eigenvalue, and all the other eigenvalues are within the unit circle, there's a wonderful trick that's used in linear algebra all the time is to annihilate the subspace corresponding to this eigenvalue, basically moving it to 0. So basically, the idea is to kill this off. So remove that eigenvalue at 1 and move it to 0. And so p tilde I define to be p minus this weird notation 1 cross pi. All right. And again, I don't need that cross, and a lot of books won't show that. They'll just write 1 pi, because pi is a row vector, and 1's a vector of 1's. And you all know if you multiply a column vector and a row vector, you get a matrix. But I know from experience that people get really confused. So that's just to emphasize, I'm talking about a matrix there, a d by d matrix. And also it's standard notation in the theory I'm going to talk about today, in Puer and Frobenius theory. It's used, because, again, for emphasis. Because if you get rid of this, it starts to look really strange. All right. All right, and the proof was, I didn't prove that all I did was move the eigenvalue from here to here. I'm just leaving that as an exercise. But once you establish that, which is not hard, we saw that, God, if all the eigenvalues are within the unit circle, we know p to the n goes to 0. And we know that, hopefully. All right. I guess I didn't prove that either, but we get this at a geometric rate, and it depends on the rate depends on how this distance between the unit disk and the eigenvalues. All right. All right. So what I want to do is first step back and explain how this fits with what a professor would normally do. And because it's quite pretty that there is a connection with the standard treatment of Markov chains. So let me do that first. Okay, so the standard treatment is to say, well, let's look at a 4-state Markov chain, and we denote the states by little, little balls like that. Okay, and then again, I mentioned this last lecture, but let's say it again. Whenever an entry of P is, and we've got our transition matrix. I need a different number for this. I'll call it capital N. Last time I called this little n, I kept on using that for time as well. So let's use a different symbol. So here, n equals 4. And so whenever an entry is positive, you draw an arrow from the corresponding nodes. So let's say the probability of going from 1 to 2 is positive, so we draw an arrow. Say the probability from 2 to 1 is positive, say. Let's say we can get to 3. From 1 to 3 is positive. From 4 to 3 is positive. And this looks dangerous. Let's say we can go back. All right? All right. So what does this mean again? So from 1, I can get to 2 or 3, and that's all. From 2, I can only get to 1. From 3, it looks like I can get to 2. And then from 4, I can get to 3. All right. So given the graph structure, you know the structure of the transition matrix, but you don't know the numerical values. All right. And so tell me, what do you think happens here? How do I relate this with my assumptions here and with this graph here? All right? So I defined unit chain to mean there's a single eigenvalue here. Do you think this is unit chain? Yeah. It's not easy to see. I mean, I'm not expecting you to compute the eigenvalues in your head. Okay, well, here's some facts. You know, the equivalence of definitions. So unit chain, again, I define that to be that the eigenvalue corresponding to 1 is unique. You know, it's not a repeated eigenvalue, it's just 1. And let me write down the definition. You mentioned the characteristic equation. All right, so this is what you do to compute eigenvalues, right? You look at iz minus p, you take the determinant, set equal to 0. The zeros are equal to, are equal to the eigenvalues. Well, this characteristic equation, of course, has a 0 at z equals 1, but it's not repeated. So B and A, it's just a more formal statement of A, in case you forget what single eigenvalue means. But C is going to the graph. And if I stare at this graph, let's take the number 1. Can I reach 1 from any initial condition? So from 4 I can go to 3, I can go to 2, and then go to 1. From 2 I can jump straight to 1. From 3, of course, to get from 4 to 1 I had to go through 3. So from 3 I can get to 1. Okay? So that's the standard definition of unit chain. That there's some state I can reach from any initial condition. It's very cumbersome to say it in terms of the graph. You heard what I just did. I said I can hop from here to here to here. Another way to say it is just to look at this infinite sum. You know, to say that I can reach x star from any initial condition just means that this sum is positive. Of course, it's infinite, but I don't need that. I mean, all I need is it to be positive for every x in x. So these three things are all equivalent. All right, and I'm going to prove it to you without really telling you so. I mean, you all can see that I implies C, right, from the ergodic theorem. A implies C. Right? Because if we've got p to the n x to x prime going to pi of x prime, wait, that required aperiodicity. Damn. Only under aperiodicity. Dicity. Okay. There's a bit more work to do, so you have to get rid of that. Okay, but yeah, I mean, a little more work, A implies C is pretty easy. And then C implies A, I'm going to prove to you only because it's useful. There's some insight there. Yep.
So according to definition C, like not that, but when you explained it,
Uh-huh.
will you be able to go from 1 to 1 as well? Like from its
No. It just, so you notice, in fact, let's put some self loops in here. Yeah, it's a mistake to avoid all these. I mean, I had an example where the diagonal was all, oh, there's a mistake here, right? 1 to 2. I think that's why you asked the question. There's a typo over here. So from 1 I can reach 2. From 1 I can't go back to myself. I have to leave. I can go to 2, and I can go to 3. So the rest is correct. Yeah. So I just stuck in a self loop just to emphasize I don't need to have diagonal 0, and well, whatever. Yeah. Okay. Yeah. But yeah. So to the unit chain definition, then you can see I don't care. I mean, it's a really useful fact because I don't care about the numerical values. Is there?
You can go directly from 1 to 3.
Okay, let's see. 1 to, no, right there's an arrow.
Okay,
Yeah.
then we're good.
Okay. I mean, it's useful to have C because it tells you don't need to know the numerical values. You don't have to solve a characteristic equation to know if you're unit chain. You just see which is positive or not. All right. There's that. In aperiodicity, you can imagine there's something similar. So the definition I gave you, I'll lump these together, it's very similar, that if you have an eigenvalue, I'm sorry, 0. So if you have I don't need those absolute value, modular signs. So there's a characteristic equation. Any 0 of this is an eigenvalue, right? Basic linear algebra, right? Which I seem to be forgetting. So if you have an eigenvalue with modulus 1, so that means that I've got something on the unit disk, right? Well, then what? There's a definition I gave last time. See, I'm defining aperiodicity. Then not that, right? Because this having an eigenvalue on the unit disk implies periodicity. So then Z naught equals 1. All right. So that's the linear algebraic sense of it. The way, if you took a standard class, they would never mention eigenvalues. And they would basically look at the graph structure. Okay, so suppose you can represent the state space as a union of disjoint smaller sets, and they have this periodic behavior. So the probability of going from x to xk plus 1. So remember when I originally defined transition kernels, I put a set here, not a point. All right? So this is the probability that xt plus 1 is in the set xk plus 1 given xt equals x. So I'm going to use both notations. I'm going to think of this as a matrix, but mainly I think of it as a transition from states to sets. Right? So suppose that that's equal to 1. For all x in the previous set. All right, and you do this for every k, but k only goes from 1 to d, so you do this modulo d. Right? So you've partitioned, you've basically got this partition of x1, x2, x3, and basically, you can just draw a gigantic arrow here. Any point here goes to some point here, and any point here goes to some point here, and so forth. All right? So aperiodicity means this can't happen. Right? Yeah. So d equals 1, x is everything, that's it. Yeah. So, yawn. And so you look at this graph here, you can see there's no decomposition because there's no way to break this up into these parts. So if you went and you put in any numbers in this matrix, such as a transition matrix, so this plus this has to be 1, that plus that has to be 1, and so forth, and type Eig in MATLAB, you will get exactly that structure. It's aperiodic and unit chain, and so you'll get that. It's amazing that you can get so much structure about eigenvalues by looking at something so basic about graphs. Cool. Now this language is not standard. It's not my fault. It's called regular. It's called all sorts of things. Unit chain is just what I've found is the most common. I've called it different things myself, but so every place you look. They call it regular at the MIT open course. Regular. Regular means so many things for Markov chains that is stupid. Don't use regular. It might be used by MIT, but they don't know Markov chains. They should read my book. Regular has like a very precise meaning, and we didn't invent it. So MIT, you screwed up. All right. All right, so, all with me? Yep. What?
What is the?
No, suppose. So suppose I have a decomposition of D sets that are disjoint and it has this, this structure. Any point here, I have to go there. Any point here, I have to go here. So this is a periodic decomposition of a Markov chain. Aperiodic means that you can't do it non-trivially. The d just is 1. So it means that all the xk's are just x. Okay.
So does this mean like the states are never growing or decreasing? Like this number of states we could transition to is constant.
Well, it just means this. I don't know how to be more precise than that.
Like we can't go to a new state that's not in the original state.
No, this is a whole state space.
Yeah.
No, but take a look. From
Is that what this means?
no, because from 1 I can only go to 2 or 3.
No?
I'm very limited. From 4 I can only go to 3. Right? I'm very, very limited. Look how sparse this graph is. Right? But this is a unit chain because I can't decompose. So the thing is, you want me to compactify it or something, but this is as crisp a statement as I can say. If I take a point here, with probably 1, I end up in one of these steps after one time step. If I take any point here after one time step, I'm in somewhere in this set. I can't make it any more compact. Okay. All right. So what I want to do is, now that you've accepted this, of course, well, what I do is we really do need this, right? We have this top eigenvalue 1, and we want to find, obviously P1 equals 1 is pretty trivial. I can compute that. I can type 1 in MATLAB 10 times for its 10-state space Markov chain, and I've done it. But look, how would you all do this in MATLAB? Compute pi. Or Python, I don't know. Yeah, I mean, how would you do it? Anybody have an efficient code for computing pi?
Make a dictionary.
No, how would you compute, it's an eigenvector problem, right? This is an eigenvector problem. How would you compute it's a left eigenvector. So basic,
Like pi.
oh, no. I mean, pi is right there. That's the symbol pi. Pi is not 3.1415926 in my course. It's,
No. I mean, like the empirical.
no, pi, right there, pi, the left eigenvector, yeah. How would you compute a left eigenvector? You know, I mean, so basically if I, again, in this matrix sort of setting, you know, I'm thinking of pi as a row vector here, right? And you could flip things around. I could say A equals P transpose, and I want to solve PV equals V, all right? And V of I is just equal to pi of I. Where now, you know, V is a column vector here, not P, but A. So that makes it more concrete. How would you all do this in MATLAB? And if you know the answer, well, tell me, what would you do? A single value decomposition would give me, singular value decomposition is for the norm, really, right? Because the singular values, I mean, I'll bet you, no, that's A transpose. Because that's the square root of the top, the eigenvalue of A transpose. And what does that give you for, I don't know if that gives you anything, sorry. How about you? Yeah, that's what I expected somebody to say. So basically what you can do is you can say, I don't remember the order in MATLAB, is it? Yeah, thank you. V comma D equals the eigen of A, you know. And I don't know what the complexity is of that operation. It works just fine. All right, lecture over. No, there's a cool, does anybody else have any suggestions? Ooh. Nice. All right. Yeah, that's not a bad suggestion. So just iterate this equation, you know. I like that. So basically you've got an estimate at stage n, and we know that converges geometrically quickly. And you know, typically the gap isn't that big. So you could probably get away with 1,000 matrix multiplications maybe in typical examples. You know, but if it was 1,000 by 1,000 matrix, there'd be a complexity, and there's a complexity n squared at each, well, P might be sparse, it might not be that bad. I mean, in this case, these things often have a lot of zeros. So the complexity of each iteration here might only be the dimension, and then you've got to do it n times, and so, you know, it has to do the spectral gap, how big you can take n. Part of the problem is you don't know when to stop, but you could look at the norm. Yeah, I mean, you stop when maybe the norm of pi n minus 1 is less than or equal to tolerance. I don't know. I'm just, you know, maybe that would be the stopping rule. Yeah. So that's one thing. This is a reasonable thing to do. It's a lot less complex than that. but this is precise, exactly. All right. Anybody else? Okay. Benius. I-O-U-S? Is that right? Benius, yeah. It looks funny. Okay, so there's this beautiful theory of Perron-Frobenius for doing this. And I'm going to give you the main ideas. It's just like a one-liner. It turns out it's a trick to convert the eigenvector problem into a matrix inversion problem. And it goes way beyond Markov chains. It's used in a lot of fields besides Markov chains. Okay? So That's what. So Peron-Fabini's theory, like the step one in their theory, or step two or something, is to convert the eigenvector problem into an inverse problem, and it's a really clever trick, and it gives you the eigenvector here at 1, and it doesn't tell you much about the others. So it doesn't give you any insight about how to compute the others, really. It maybe gives you bounds on how far away they are and stuff, but that's about it. So, but it's fun. I mean, you'll see it. It's cute. All right? Also, it doesn't require aperiodicity. So here, for this approach to work, you need aperiodicity. You know? Actually, this would fix your problem if you did a bit of averaging. So basically, you take your previous guys and you average them and then hit it by p. This then would even work in the aperiodic case. Something like that. I mean, you can go in. Anyway, there's lots of ways to make it periodic. I won't go into that. So here's the trick. So let's go back to our graph. And I want to identify all the states that are reachable. What did I? Oh, scheiße. So X star is a set of reachable states. So we're sticking to the unit chain case. So all right, so we can stick to that throughout. All right, so we've got that graph structure like right there. And so I'm going to let X star be the set of all points that are reachable from everywhere. Right? And that's actually equal to the set of all X such that the sum k equals 1 to infinity I don't have to say for all x naught. I can just pick one x star which is reachable. All right? So look at this graph, because if you can see it, because it captures everything. What is it here? You know, I said I could reach 1 from any initial condition, right? All right. From 1 I can get to 2. So therefore I can get to 2 from any initial condition. From 2 I can only get back to 1. But from 1 I can get to 3, and so therefore I can get to 3 from any initial condition. Poor 4 is lost, you know. Once you leave 4 you can never get back. So it's just a wasted state. All right. So it's basically just the 3 points. Let's just leave out 4 because it can't be reached. Yeah? All right. So basically, that's an irreducible subset. So I can go from any state to any other state. I forgot to define irreducible. I talked about this unit chain thing. Irreducible just means you can get from any state to any other state. You know. All right, so I don't know. I won't use that term again, so don't worry about it. All right. So what I'm going to do is this. I'm going to go through a very careful construction. I'm going to choose you give me a probability mass function on X star.
The only thing is when you press
so first of all, I want a probability mass function X star on this set. It doesn't matter what it is, anything you want. And secondly, I want a function yeah, it doesn't have to be an X star, but I'll do that. I've got a function which is positive, it's not identically, it's non-negatively valued, and it can't be identically zero. I've got a probability mass function on this. And fluid, it has to solve a minorization condition. This is a Perron-Frobenius trick. All right, so this has to be constructed. It might be really hard, maybe not, we'll see. But so I've got this, it's called a minorization condition. All right, and given my love of compact notation, how am I going to write this? The right-hand side, the left-hand side's a matrix, right? That's what I keep screaming at you. The right-hand side must be a matrix as well. Doesn't it look like my my 1 cross pi business? Yep, it's an outer product. It's S cross nu. S, think of functions always as column vectors, and probably mass functions as row vectors. So the way you'll find this in textbooks is this. And yeah. Okay, so I should tell you some background here. There's all these books on Perron-Frobenius theory. The gem is Numland's book, even though it's 1,000,000 years old. It's a tiny book about that thick, and the appendix of my networks book has a survey as well. But basically, this S cross nu. Remember, I told you that cross is just a funky thing. You can get rid of it. It's a column vector times a row vector. That's a matrix. And I'm saying the greater than sign is not in terms of positive definiteness. It's just entry-wise. The entries of this matrix dominate the entries of this matrix. All right. That little trick of domination makes just like this computational thing just like a one-shot thing. And I'll show you that. I'm gonna leave out a few details, or maybe not. Yeah, we'll see. I mean, you can get a beautiful formula for pi just based on the minorization. And once you get that formula, it leads to ways of getting bounds on cost functions, things like that. Okay, you ready? No? Okay, so this is the stuff you gave me. Oh yeah, I should give you an example. Take S just to be 1 if x equals x star and 0 else. And what am I going to take nu of, say, x prime? Well, this is 0 everywhere except for one state. So I only have to worry about when x is that special state. Right? And for that, I've got p sitting right there, so I can get equality. All right, so it's legitimate to ask me, why did I make this abstract when I can just write down an answer? And the reason is that when you put it like this, it'll be really obvious that this has nothing to do with a finite state space. This could be a general state space, it could be anything, all right? I mean, nu won't be a probability mass function, it'll be a probability measure, you know? And I won't write x and x prime, I'll put a set there and a set there. So with this abstract notation, finite, countable, Rn, it's all the same thing. All right.